Welcome to everyone at the far distance. I hope everyone is in good health. Today I'm going to talk about the structure of the eye. Everyone recognizes that this is far from the human eye, but the very complex beginning of the eye development during phylogenesis. The human eye is a beautiful thing. Practically, it consists of, the visual organ itself consists of three different components. One, the most important one, everything is important, is the eyeball situated in the orbit, and there is a tract connecting it with the brain itself. It begins with optic nerve and continues after the optic chiasm as optic tract, as well as there are very important accessory organs ensuring the proper function of the visual organ. These include the eyelids, the superior and inferior eyelids, the conjunctiva covering the anterior surface of the eyeball. These things serve as mechanical defense to the eye. The lacrimal apparatus is the one which also serves as defending system, but the important function of it is to keep the anterior surface of the cornea wet, which is covered by stratified non-keratinized epithelium, which is not supposed to dry out, as well as there are the muscles responsible for the very delicate movement of the eyeball, just directing the gaze of the eye. Going into details of these things, starting with the eyeball, there are outer characteristics of it. This one is a right eye viewed from above, on which you can see the spherical shape of the eyeball, as the name reflects, from which anteriorly a small portion protrudes more, having a smaller radius of curvature, and this anterior part of the eyeball is the one which is completely transparent. That one is called the cornea, separated from the rest of the outer coat of the eye. This is called the sclera, and the groove of the sclera in which the cornea fits. Optic nerve starts not from the posterior end, but slightly shifted medially from it, and goes to the hypothalamus. We distinguish two poles on this spherical organ, the anterior and posterior. Connecting them, we end up with the axis of the eye. Important to mention that axis of the eye is not the same as the optical axis, as the light goes through the eyeball, since the place of the retina, of the innermost coat of the eye, where the very sharp perception of the visual influence is made, this is called the fovea centralis. This one is shifted slightly lateral to the posterior pole, therefore this optic axis closes an angle with the axis of the eye. Considering the axis of the orbit, again another deviation should be mentioned, since the optic axis and the axis of the orbit closes something like 23-25 degrees because of the lateral anterior orientation of the axis of the orbit, as you remember it from the first semester from knowing the skull. Just to make easier to locate something within the eyeball, ophthalmologists should, and also you, should divide the eyeball into anterior and posterior halves, constructing the frontal plane. This one is goes to the equator of the eye, so in the middle of the eye, that separates anterior half from the posterior half of the eye. Perpendicular to this, a horizontal meridian, so the other places perpendicular that are the meridians, like the meridians of the earth itself. So the horizontal meridian divides superior and inferior halves now. By these two planes, 4 quadrants are produced within the eye, and perpendicular to each of the previous ones, the vertical meridian divides the eye into nasal and the temporal parts, halves, but if you consider all the planes, octants are produced. To name an octant, you should combine three different adjectives with each other. For example, that should be the anterior, nasal and superior octant of the eye. Structural layers of the eye. You should consider the eyeball as having three different concentrical layers fitting into each other. The outermost is tunica fibrosa. As the name indicates, the dominant structure here is the dense collagenous connective tissue, but two different components this tunica fibrosa has got. As we mentioned before, the anterior transparent part of it, this one is the cornea. The rest, the majority of tunica fibrosa, is the sclera. The inner inside of this, the next tunica, is tunica vasculosa, indicating that this is responsible for the very rich blood supply of the innermost layer, the innermost coat of the eye. This consists of three different parts: the iris, the ciliary body, and the choroidea, as we are going to see later. And the innermost layer is tunica nervosa. This is the same as retina. So that is the part of the eye which can perceive the photons of the light, as well as start to process the optic information. Other components are the ones which, if you want, make the core of the eye, fill up the inner space of the eye, and these are the things through which the light goes before it gets perceived by the retina. These are the anterior cornea, as we mentioned before, but that is part of tunica fibrosa. After that comes eye chamber containing water-like fluid, and through the eye chamber the light transmitted to the lens, which focuses the light as well as turns it over. So according to that, when the light finally goes through the rest of the core of the eye, this is called the vitreous body. So the perception of the image of the surrounding is upside down, projected onto the retina. Tunica fibrosa, so going into details, I start with the sclera because even if it lies behind the cornea, but because this is makes a bigger proportion of tunica fibrosa. As the name indicates, it is made up of dense collagenous connective tissue, not equal thickness. It has got thicker, it is next to the exit of the optic nerve from the eyeball. Don't memorize these measures, these numbers of the millimeters. The optic nerve goes through necessarily, because it comes from the retina, goes through this sclera, making perforations on it. So several small holes transmit the optic fibers, and therefore this is called cribriform plate of the sclera, not to be mixed up with cribriform plate of ethmoid bone. There are several other structures which must pierce this tunica fibrosa, the sclera. Arteries, both anteriorly and posteriorly, entering into tunica vasculosa, as well as veins should leave from the eyeball by piercing it at 4 different places. The histological structure that this image shows to you, so this is a very easily recognizable dense collagenous connective tissue. Outside of it, someone can recognize skeletal muscle, so this belongs to extraocular eye muscle. Inside of it, the next 2 layers would come, so this is the thing you should concentrate to. Cornea has extremely delicate structure. It is embedded or in a groove formed by the sclera. This is the corneal sclera sulcus, and it is inserted into this like the glass of the watch, the hourglass. So the middle of it exceeds the outer and inner margins, so that it has a very firm fixing of the cornea. Also, the thickness varies, of course, where the light must most go through when the cornea has the smallest thickness and becomes wider at the ends, at the lateral ends. Altogether, the diameter is 13 millimeters. The histological structure I'm going to tell now, anteriorly necessarily it should be covered by epithelium. This epithelium must be quite strong, but should not dry out through stratified squamous keratinized epithelium, not much light can go. Therefore, this epithelium is a stratified squamous non-keratinized epithelium, as you can recognize very nicely on this layer. You can also recall the sublayers of this epithelium. This is the cornea epithelium. It has got some unique characteristics, unique features, like it is very richly innervated by type C, so the thin myelinated sensory fibers. These free nerve endings within the epithelium protrude, as well as the base of the epithelium, as you can see, completely lacks those protrusions of the underlying tissue, which were always seen at all the other places. These were the connective tissue papillae. So there are no connective tissue papillae beneath the epithelium of the cornea. This is again so it has got a function with the linear, very nice, unbroken transmission of the line. At an irregular border, of course, the line would be deviated to one and other directions. Deep to it, as everyone can expect, a basement lamina should come, and this basement lamina is very nicely, clearly visible, so unusually thick basement lamina beneath the epithelium. This is the anterior limiting lamina of Baumann. The same guy was naming the capsule in the kidney. And then comes the thickest layer. This one is the proper substance, the substantia propria, or also called stroma, of the cornea, which should be lined by another type of epithelium on the posterior surface, this posterior surface, but because the anterior eye chamber is full of liquid, therefore the epithelium is needed here. This epithelium should be thin enough, so weak enough, and therefore the thinnest epithelium does well. But between the substantia propria and this epithelium, again, lamina propria should be present, and this lamina propria is again extremely thick layer. This is called the posterior limiting lamina of Desame, and then comes the very weak epithelium, in fact the endothelium of the anterior eye chamber. So these are the layers. And going into details of this, very nice illustration of Professor Kirstich I'm showing again. You can recall the previous things we mentioned. Anteriorly is the epithelium with the type C afferents within, then the anterior, the Baumann's lamina comes, and then comes the very thick substantia propria, and the structure after that, the inner, the Desame membrane, and the endothelium comes. And the tricky structure of substantia propria is the one which is responsible for the transparency of this practically dense collagenous connective tissue. As you can see, it consists of several layers packed deep to each other. In one of these layers, the collagen microfibrils are strictly parallelly organized with each other. In the other layer, the subsequent layer, again parallel with each other but perpendicular to the fibers of the first layer, they run, and then comes again an orientation of the fibers corresponding to that of the first lamina, and after that several laminae, something like 7 laminae altogether, make up this substantia propria. In this laminae, the parallel organization you can see very nicely with each other in the cross-section of electron microscopical picture of one of these laminae, and comparing it with the orientation of these collagen fibrils in dense collagen connective tissue like in the sclera, you can see one big difference. One is the equal diameter, very unique equal diameter of all the fibrils in the cornea, contrary to the varying diameter of the fibrils in the dense collagenous connective tissue. Another important thing is the unique fibrocytes, if you want. In between these laminae, they are flashed, squeezed. In a light microscopical picture, someone would recognize the shape of the fibrocyte, the elongated nucleus with sharp edges. But if you consider in three-dimensional space these fibrocytes, these are again unique because strictly in one direction processes start, in the opposite of course, another direction, and when they branch at a right angle. So either parallel with the one of the fibers of the one of the layers they go, or perpendicular to it. So that is a very unique shape, which therefore the cells, these fibrocytes, deserve their own name. These are the keratocytes here, and again these are in serve of the transparency of the cornea for the light. The anterior and posterior limiting laminae, these extremely thick layers of basement membrane, these are for the complete hermetic sealing of the delicate tissue of the substantia propria. The importance of these layers can nicely be seen if there is a damage to the anterior limiting membrane. The foreign body goes through, and deep to this damage, if the damage is penetrating through the anterior limiting membrane, deep to the damage, the cornea loses its transparency. In electron microscopic picture, you can see the same as previously projected. With the flattened keratocyte appears like that, and the strictly parallel organization of the fibrilles, and perpendicular to this, the cross-section shows the adjacent laminae. As for all the connective tissues, of course the amorphous substance is an important component. Something like 10% of the dry components, the proteoglycans, equal to, which have the same structure and same components as for other the dense collagenous connective tissues. The unique thing here in the gags, the proteoglycans, is the keratin sulfate. Helps the function of the cornea being transparent. Dermatan sulfate, which is not only for the cornea, unique, found in every dense collagenous connective tissue. There is a specific staining, the cupromaronic blue, which reveals cross bridges, proteoglycans between these microfibrils, and these are the things which keep the constant distance between the microfibrils themselves. About the endothelium of the anterior eye chamber, nothing to be said. Everyone recognizes the flattened oval nucleus parallel with the surface. This is a weak endothelium there. Next layer comes the tunica vasculosa. Tunica vasculosa, as listed before, consists of different components. Again, starting from behind, just because this makes the majority of the tunica vasculosa. The choroid is to be discussed now. Related to the innermost layer, but should be mentioned now, there is a strict circular line at the eye, fitting in the frontal plane, so dividing the tunica vasculosa into an anterior and a posterior bigger part. This one is called the ora serrato. That is a line on the retina, but should be mentioned now. In front of it, the retina is blind. Behind of it, the retina is able to perceive the light. So behind the ora serrato is choroideo, or just choroid itself. This one, as the picture shows, has got extremely rich vascular supply, and this supply arises from short posterior ciliary arteries piercing the sclera next to the optic nerve. According to that, of course, long posterior ciliary should should go through the sclera, but more goes anteriorly. As well as there are anterior ciliary arteries, smaller in size than the others, but equally important, and they anastomose with the long posterior ciliary arteries. As well as veins are the ones which collect the blood from this tunica vasculosa, and these veins, first of all, there are 4 major veins according to the 4 different quadrants of the eye, piercing the sclera. Believe or not, I've seen these veins. I'm a strong smoker, and during the night in total darkness when I'm coughing, I have 4 flashing lights according to the exit points of these vorticose veins. These are called vorticose veins because of the whirling course of them. Also there are veins collecting blood from the anterior part of the tunica vasculosa, and these pierce anteriorly the sclera and join episcleral veins. So these are practically the holes on the sclera through which the vessels enter. Again, an illustration from Professor Kirstich shows part of the sclera here, as well as part of the retina here. So that is outer, this is inner aspect of the small piece of the complete eye wall, and we should concentrate to this one because that corresponds to the tunica vasculosa. It has got several layers you should know and you should recognize on the histological slides. The first layer lies just deep to the sclera, and as you can see, it is full of melanocytes. This is called the lamina suprachoroidea. This is quite a controversial name because supra means above, so it tells you that it's a layer above the choroidea. The other name is lamina fuscoscleri, again indicating that rather it belongs to the sclera than the tunica vasculochoroidea, but we describe it as a first layer of choroidea. Now the presence of melanocytes, first of all, the melanocytes make the deep brown color of the uvea itself, and this is what fusco means, deep brown. So this comes from the presence of melanocytes, and the animals moving at the night. This one is the picture taken from the cat of Professor Sétáló. They extremely reflect the inflowing light from the eyes, and that is due to the presence of melanocytes. Deep to it, the lamina vasculosa comes. So tunica vasculosa has got a lamina vasculosa consisted of or containing many vessels. These belong to the medium-sized or even smaller arterioles and venules, someone can recognize. So that's where the vessels are distributed. Here venules, you can see arterioles, you can see, and these finally branch in an inner sublamina of the choroidea, and that is called the lamina choriocapillary layer, or lamina choriocapillaris, indicating that these ones are really capillaries here. Deep to it, the last layer is a basement lamina again. This one is lamina basalis, or the Bruch's membrane of Bruch, he was naming it. Do not mind the abbreviations, the small abbreviations on the picture of Professor Kirstich. Just look at the beautiful illustration of the extremely nice and rich capillarization on the surface, outer surface of the retina. That is the choriocapillary layer. From here, the rest of the wall of the eye has been imaginarily removed. And this picture roughly shows you that at almost the same degree as the capillarization on the surface of the alveoli of the lung, you can see the rich capillarization on the surface, outer surface of the retina. Here, corrosion electron-microscopic or scanning electron-microscopic picture shows the same. So practically most of the retina gets contacted through the Bruch's membrane, of course, gets contacted with capillaries, and the one which is left free. If you consider this contact with the retina, here the inner layer is that one is the retina here. So these capillaries have got fenestrated endothelium, of course, so letting the exchange of materials much more fast going. Red blood cells could be recognized here. Embedded in the basement lamina, this is a green thing. There are some pericytes which are here, or melanocytes, having the melanin granules. Someone can recognize nerve fiber bundles here and bigger veins in the outer layer, so these venules in the outer layer like this. and deep to the basement lamina of the capillary endothelium. Another basement lamina separates the outermost layer of retina from the capillary. So through these layers, all the materials should go. Anterior to ora serrata, again you can see part of the ora serrata. This one is back view of one of the eyes, doesn't matter which eye. Someone can recognize the lens, anterior corneal, having the greater curvature of its surface. So that is back view. Also enlarged from here, a back view is seen here, or in other illustration, completely posteriorly looking at, you can see that, and higher magnification here. So going into details, there is a peripheral margin of this ciliary body, which has got radiaire, of course, so oriented to the anterior pole of the eye, radiaire folds, and these are called the ciliary folds. All this zone is called the orbiculus ciliaris. This is the outer layer here. Inside of it, not the outer part, inside of it, the ciliary folds continue into much more delicate protrusions, but having the same orientation, radial orientation. These are called the ciliary processes. Here you can nicely see these processes in the posterior, and also here you can recognize the delicate processes. The next component of this, in between these ciliary processes, delicate collagen fibrils attach or are anchored, and these are the fibrils which keep the lens in position. So in other side of the fibril, it is anchored in the capsule of the lens. So these are the things keeping the lens, and these are the zonular fibers of Zinn. Zinn was naming them. In between these, because the orientation of these fibers is very unique, again having the equal suspension everywhere of the lens, the ones which come from anterior side of the ciliary body go to be attached to the posterior surface of the capsule of the lens, and the ones which originate from backward to the anterior surface of the capsule, they insert. So by crossing the fibers with each other, there is a space which goes around the lens everywhere, and this is called the canal of Petit. And of course it should contain the same fluid as the space everywhere around. The biggest mass of the ciliary body contains ciliary muscle, and this function of ciliary muscle is that it can vary the convexity of the lens according to the different accommodation of the lens. The important function of the ciliary processes, so these things we are talking about, enlarged here you can see them, is to produce the fluid into the posterior eye chamber. This one is the aqueous humor, and therefore here another barrier is to be mentioned, in addition to several other barriers you've heard before. So this is the blood aqueous humor barrier. From capillaries, how the aqueous humor is produced into the posterior eye chamber. The layers are first the capillary endothelium, which has got fenestration. Also the basement lamina of it should belong to this barrier. Then basement lamina comes again because there is a specific type of epithelium on the inner surface of the ciliary processes, and that is the continuation of the retina anteriorly, but the retina here only consists of two different layers, contrary to the visual part of the retina, which has got 10 layers. Here there is only an outer pigment layer and an inner non-pigmented layer, epithelial cells of course, kept together by zonular junctions. As always, the epithelial cells are kept together by this, so making the hermetic sealing. That is the function. And what you can recognize beautifully, you can see on this big drawing, both on the outer surface of the pigmented layer of the retina and the inner surface of the non-pigmented cells, there are extreme invaginations, extremely complex invaginations of the membrane, of the surface membrane. These make basement labyrinth. And if you remember to the kidney, for example, when the same structure was found both in the proximal and distal convoluted tubules, together with the mitochondria, the numerous mitochondria, they're viewed in everywhere. The basement labyrinth plus the mitochondria are equal to a basal striation. And if you remember the function of basal striation, that is responsible for active ionic transport. So according to that, active ionic transport is the way how aqueous humor is produced through these layers of the barrier. Ciliary muscle is to be explored now. The ciliary muscle consists of smooth muscle, and therefore the very frequently made mistake, always we usually call them fibers. It is a mistake because the only muscle consisted of fibers is the skeletal muscle. So these are all smooth muscles. Keep in mind, even if you say fibers, you should mean the smooth muscle cells, of course. But these cells have got three different orientations. The outermost cells are parallelly running with the inner surface of the of the sclera, and these are according to that meridional fibers, so following the meridians of the eye. More inner cells are directed towards the core of the eye, towards the center of the eye, and therefore radial muscle cells, we should mention them. The innermost cells are arranged in circles, so according to that they act as sphincter, and these are the circular muscle cells. The outer was described by Brücke, the inner by Müller, and these terms are necessary for the clinics, not for the anatomy exam. These are the eponyms. Here again you can see the circular passage full of aqueous humor around the edge of the lens, and that is the petit canal of Petit. Now, how these muscles can act and what is the function of them. First, the easiest to understand, how the circular muscles, when they contract, they act as sphincter. According to contraction, of course, the diameter of the structure gets smaller, and due to this smaller diameter, the lens becomes more convex, and this more convex lens is needed for the close accommodation of the eye. Also the meridional fibers, because the meridional fibers, when they contract, the anterior attachment of these cells should be considered as more fixed. So according to that, anteriorly they can pull all the complex ciliary body, the complete ciliary body, and doesn't matter which direction from the vertical meridian we go, both anteriorly and posteriorly, the diameter of the eye becomes smaller. So the biggest diameter it has got in the frontal meridian. By pulling all the ciliary muscle anteriorly, of course the diameter of it again becomes smaller, and that ends up with the more convex lens. The third, I think, not so easy to understand, the radial fibers. The radial fibers should be considered as being parallel with the base of all the ciliary body. And if you make narrower a triangular structure, then of course the triangular structure necessarily should be higher. From both sides, if you consider, of course, the complete circle, the diameter of the complete circle gets reduced, so again the final result is making the lens more convex for closer accommodation. So it doesn't matter which component of the ciliary muscle you consider, the contraction of the cells is resulting in the decreased convexity of the lens. Finally, the last part of the tunica vasculosa, the most anterior part of the tunica vasculosa, because of its beautiful appearance, freely visible through the transparent cornea, because of that, the name of it is the iris, resembling to this flower. And this iris is a diaphragm-like flat membrane, according to that having two margins, When it is attached to the ciliary body, this one necessarily called the ciliary margin, and it leaves an opening at the center, and that is the pupil, which transmits the light through which the light can get into the retina. Looking at the histological picture of course, one half of the iris is shown here. Behind of it, someone can recognize the lens. We did not talk about yet. Okay, so the most striking thing is within this connective tissue, loose connective tissue, someone can recognize muscular tissue, and this muscular tissue practically consists of two different types of muscles. One is not even a muscle. So this is iris showing the different layers of it. Anteriorly, it is covered by a layer of flattened, modified fibrocytes. So between them there are holes, therefore even if the cells resemble to endothelial cells, these are in reality fibrocytes. Behind of that comes the stroma of the iris, having beautiful blood vessels, which really inside correspond to capillaries, but unusually thick walls they've got. And behind of them, here you can see these circularly oriented smooth muscle cells are. And of course, because they are circularly going by contraction, they can reduce the diameter of the pupil. So this should be called the sphincter of the pupil, sphincter pupillae muscle. Behind of it, there are contractile processes, but these processes are radial processes of pigmented epithelial cells. So we should consider this as a myoepithelium. The smooth cross-section of the smooth muscle of this sphincter pupillae is freely recognizable here, and behind of it, a very narrow layer in front of the pigmented cells correspond to these radial processes of these cells, and this should be called the dilator of the pupil, dilator pupillae muscle, but keep in mind that these are myoepithelial cell processes. These two muscles are under control of different parts of the autonomic nervous system. The dilator pupil is controlled by the sympathetic nervous system, and the opposite applies to the parasympathetic. So due to parasympathetic stage of the body, the pupil becomes smaller. If you want to memorize, people used to say that when people are in fear, their eyes get open wide. This is not really the eye, but the pupil which enlarges when the sympathetic situation exists. Talking about a couple of words of these specific types of capillaries seen here. So the inner layer of them corresponds to the normal structure of capillary, with endothelium, with pericyte embedded in the basement lamina of the endothelium. But outside of it, there is a very thick sheet around the capillary, consisted of fine collagen microfibrils. These have got two different orientations, not important, but the importance of this collagen fibril sheath can nicely be understood if you consider the different thickness of the iris itself. When the pupil narrows, then the tissues get compressed, of course, and due to that, the capillaries will be compressed. And just keep the capillaries open, this collagen fibril sheath is needed. This is a very nice illustration of the structure of the iris. Here you can see it viewed from the back and anteriorly, and this one is the back side, somehow reflected. The most anterior part is the one which consists of these modified fibrocytes, having different degree of pigmentation. In brown-eyed people, of course, the heavy pigmentation is responsible, and almost lack of pigmentation makes the eye blue. Deep to it comes a layer of meshwork of different vessels, and these vessels, the arteries, make two different anastomotic circles. One is close to the ciliary margin of the iris, and this one is the greater iridical circle. This was major arterial circle, And close to the pupillary margin there is a smaller, not complete circle. This one is the minor arterial circle. Coming more to the back side, someone can recognize the sphincter as well as the dilator of the pupil, and looking from the inner aspect of the iris, it is reflected. You can see how the retina, by two layers, spreads onto the posterior, continues onto the posterior surface of the iris. Structure of iridocorneal angle, it needs a discussion because that is a very tricky point where the aqueous humor is able to leave the eye. And this iridocorneal angle can easily be found if you look at the histological structure by finding an endothelium-lined, quite wide cavity at this angle, embedded in the peripheral part of the cornea, and this one is called the Schlemm's canal. And the Schlemm's canal drains the aqueous humor from the anterior eye chamber. First, in between these delicate processes, here you can see the fine trabeculae covered by, again, modified fibrocytes, not epithelial cells, which somewhere leave the inner structure, the collagen microfibrils, with some very fine, delicate reticular fibers, so leave open, therefore is not epithelium, as well as continuing outside, there is a spongy zone, and through the spongy zone, the aqueous humor is released into the Schlemm's canal. From the Schlemm's canal, episcleral veins take the aqueous humor through venae aquosae, aqueous lens. These tendons, which are again, this is the wrong name for the tendon because smooth muscle, the meridional and radial cells of the ciliary muscle have got no tendons, of course, but this is the place where more fixed these smooth muscle cells are, therefore the meridional fibers can pull all the ciliary body more to the front. The spaces in between these fine trabecules are called the fontanel spaces, and finally the aqueous humor can be released from the eye. Thanks for the attention.